Hey guys, welcome to another week of linear algebra. Well, in this week we will be talking more about problems, about linear algebra problems, more about eigenvalues. And in fact, today I will even talk about the rank of a matrix. By the way, I have a question for you. Did you see the videos from last week? I did some other 2 videos. I think there are 4 in total so far with linear algebra. Did you see them? Did you have a chance to look at them? Jack, did you?
No, I didn't have a chance last week to look at them.
Okay. All right. Anyway, so there I did a bunch of problems there, like with matrices of sizes 2 and 3. Anyway, let's get started. Well, today I would like to talk about eigenvalues, eigenvectors, and like I said, about the rank of a matrix in a much more general setting, not just for 2 by 2 or 3 by 3, but you will see that the situation is something somewhat similar. All right, so we'll talk about today about eigenvalues, eigenvectors, and the rank of a matrix. So that's the topic for today. So let me do some theory because I taught this linear algebra class here at TTU, and I know exactly what I should cover, what I covered, and what I did not cover. And this thing about the eigenvalues and the eigenvectors. So we'll start. The first one is eigenvalues and eigenvectors. So let's start with this. Now, recall the definition. Probably some of you already know it, but anyway, let's recall it. So definition, we say that this number, the number lambda, right? This complex number lambda is an eigenvalue it's an eigenvalue of A of the matrix A. So the matrix A is an n by n matrix this time. If there exists a non-zero vector, in fact, if there exists a non-zero vector x, and this time I want to write it because I want you to see, so it's a column vector, right? Let me point this out. So it's a column vector. Right? Such that the following equality holds true. And let me write it like this. So such that A times X is lambda times X. So this is the definition for an eigenvalue, right? Well, there are some properties about this, and before I go and talk about the properties, we'll denote this spec of A. That will be the notation. So this is the set of all eigenvalues of A. So this is the set of all eigenvalues of A, right? So that's what we this is how we denote them. So the spectrum, this is what we call this the spectrum. Okay, and now before I even talk about well, as you know by now, I would like to talk about how to get these eigenvalues. So these eigenvalues are can be obtained by the from the characteristic polynomial. So also let's consider the characteristic polynomial of the matrix A, which is given by, let me remind you that this is nothing else than just PA of lambda, which is, if you want to say, is the determinant of lambda times the identity minus A. But you can also write this in the following way. You can write this as -1 to the n times the determinant of A minus lambda n. Right? This is the, and moreover, this is given by, well, in fact, let me write it like this, which can be written, can be expressed as PA of lambda. This guy will be nothing else than just lambda to the power n, and I'm going to write it in this way, times this coefficients, sigma 1 times lambda to the power n minus 1. And you'll see that the sign will alternate here. Sigma 2 times lambda to the power n minus 2, and we keep going, plus -1 to the power n minus 1 sigma n minus 1, right? Plus -1 to the power n times sigma n. And now the question is, who are these coefficients? Where, and I'm going to write here so that you can see, where this lambda, the sigma case, these are the sum. So all these are the sum of all diagonal minors of size k. This is important. So in other words, we can say that the diagonal minors of the sum of all diagonal minors of order k. So sigma of 1 will be what? Will be the sum of diagonal minors of order k. So this will be nothing else than the sum from I to n of aii, right? Or this is nothing else than just the trace of A. Wow. So this coefficient, the first coefficient, so the coefficient of lambda to the power n minus 1 is nothing else than just the trace. But also I can write sigma 2, and this will be nothing else, this sum. So it will be the sum over all I and j, with I strictly less than j, of these determinants. So this will be aii, aij, aji, ajj. Right? So it will be the sum, or this is the determinant of this. So this is the minor. So we can also write this as, if you want to do the algebra here, so this would be aii, ajj minus aij, aji. So this will be the sum of all minors of size 2. So this is the sum. This is the sum of all minors of size 1. Size 1. and this is the sum of all minors of size 2. Keep that in mind. And we keep going, and at some point, the last coefficient, so sigma n, will be nothing else than just the will be the determinant of this. Right? Okay. Because the sum of all, this will be exactly of all minors of size n will be nothing else than just the determinant, right? That's basically the definition of the determinant. Okay, now the question, we want to address the following question. Because we have seen who are these coefficients, right? You see them here. So we know who this guy is. So this guy is the trace of A. We know who this is some, we know who this is. So we know these guys here. So we know them. And this is the determinant of A. But now the question is, these are the coefficients. Well, the question we want to address is the following. What is the relationship between a characteristic polynomial or moreover, I should say about the coefficients, basically, of the characteristic polynomial, maybe I should say, and the eigenvalues of A. That is the question. And all right, let me remind you something from polynomials, from lecture, I think it was week 2, if I remember correctly. If I have these complex numbers, lambda 1, lambda n, let's say, so these are in C, are the eigenvalues of A. Okay, then we know that P, then the polynomial, P can be decomposed as the following. So you know that P of lambda will be nothing else than just, well, it's the coefficient, the first coefficient, but it's 1, so it will be lambda minus lambda 1 times lambda minus lambda 2 times lambda minus lambda n. So after expanding all this, so if you want to multiply this product here, guess what? You will get, so expanding, so after expansion, we get the following relation. So you expand this product, and you'll get that P of lambda can be written as, and you'll see something here, lambda to the n minus, let's call this the first sum, S1 times lambda to the power n minus 1 plus S2 times lambda to the power n minus 2. And we keep going, plus -1 to the power n minus 1 times Sn minus 1 lambda plus the last one, -1 to the power n times Sn. And now we can identify the coefficients. Well, it follows that S1 will be sigma 1, S2 will be, so by identification. And we also have, but before that, and we also have that, let's see, what do we have? So we have that S1. Let's see, what was this? It was, okay, no, before that. So we have this. So this would be the sum of the eigenvalues, right? right, by Viet relations if you want. S2 will be so the sum of lambda I lambda j, and we keep going. Okay, I'm going to go like this. Sn, the last one, will be nothing else than just a product. Lambda I. Okay, and now we can identify. So now by identification, we have that S1 is lambda 1. Oops, sorry. Sigma 1, sorry. S2 is sigma 2. Sn is sigma n. Right? And now you can say that so we can say that the trace of A is the sum of the eigenvalues. In fact, let's write it here. Trace of A is the sum of the eigenvalues. The trace of the adjugate, this guy will appear again, is this sum. Lambda I lambda j. And we keep going. So the very last one, so which is the determinant of A, which is nothing else than just the product. Okay, so this is what you need to know, right? And now let me give you something which is very useful in applications, and I think we've talked about this. This is what we call the spectral mapping theorem. The spectral mapping theorem, right? So it says the following. I think I mentioned this last week as well, but let me do it again. Let A be an n by n matrix with not necessarily sorry about that, distinct eigenvalues lambda 1, lambda 2, all the way to lambda n. And let the P of x, let's say, or P of lambda, maybe I should say. All right, let me write P of lambda so that P of lambda be a polynomial. Then the eigenvalues of the matrix P of A are P of lambda 1, P of lambda 2, and we keep going, P of lambda n. So that's the spectral mapping theorem. So as an example, let's see. Examples. The first one, if A is invertible, well, even for invertible matrices, then the eigenvalues of the inverse of A inverse are 1 over lambda 1, 1 over lambda 2, 1 over lambda n. For another example, let's say for the eigenvalues of, let's say we have this matrix, the power k, so a to the power k are, so if lambda 1, lambda n are the eigenvalues of a, then the eigenvalues of a to the power k are lambda 1 to the power k, lambda 2 to the power k, and all the way to lambda n to the power k. All right, I think it's quite clear. Well, in this case, it's quite clear we have the polynomial p of lambda is lambda to the power k, so I think it's quite obvious. The spectral mapping theorem, it's amazing. I mean, you can apply it, and you have already seen that we have applied it in different circumstances last week. All right, now let's talk about special type of matrices. And moreover, I'll be interested to see what kind of properties do they have with respect to the eigenvalues of the matrix. So I'm going to divide this. I'm going to draw the following chart. All right, I'm going to put here, this will be Mn of R. So I'll have matrices with real entries, and here I'll put Mn of C with complex entries. And the first type of matrix is Hermitian. Now let me put it like this. Let me change. So this is C and this is R. So Hermitian, this is for complex entries, which means that A equals A star. And by the way, the A star is the adjoint, so is the transpose conjugate, right? So you take the transpose of the matrix A, and you conjugate each element if it has complex entries. In this case, in the case of real entries, we don't need to conjugate anything, and we'll call this symmetric. And this will be when A is the same as A transpose. Now, okay, this is the first type. Now the second type, maybe I should have drawn another chart to say a few things about the eigenvalues, but anyway, maybe I'll say it separately. The skew Hermitian which means that A is negative A star, and here it's called antisymmetric, which, as you can imagine, this means that A is negative A transpose. And now the third category, important category, we call this unitary matrices. So unitary, which means that A times A star is the same as A star times A, which is the identity. And for real matrices, we call this orthogonal. Right? And this would be A transpose is the same as A transpose times A, and it is the identity. Well, let me put another one then. Normal matrices, so normal, which is a bit different than this, which says that A star, sorry, is the same as A star A, but without being equal to the identity. And now, for normal matrices, well, we'll translate this for real is the same as well, normal, but this time will be AA transpose is the same A transpose times A. All right, so these are the type of matrices, the special type of matrices that you will see. Now let's talk about some, let me just point out some facts here. The first one, in fact, let me write them with a different color. The first fact is that all eigenvalues, unfortunately, I'm not going to prove any of this. I mean, it's a linear algebra advanced course at this point. All eigenvalues of a Hermitian, in fact, I think I proved some of them in my class, but anyway, of a Hermitian matrix are real. This is important. And also, so for all eigenvalues, of a skew Hermitian matrix are pure imaginary. And the third property is that all eigenvalues of a unitary matrix they're on the unit circle basically, so have absolute value equal to 1. That's what you need to know. Okay, so these are the facts. Well, I'll leave it to you as a question. What happens with the eigenvalues of a normal matrix? So, well, it's quite clear, I believe, I hope. Okay, now, what else should I be talking about? Let me talk about, okay, so we defined the characteristic polynomial. Let me talk about the minimal polynomial of a matrix, because I would like to use this, the minimal polynomial. And I'll give you an example of a matrix. So let me consider a matrix A. So this would be a matrix with complex entries and an n by n matrix, right? And we say that the polynomial and we'll define it in this way. I'm going to see min A of A, or if sometimes, or you can write it M of A if you want. This is the same thing. So we say that this this polynomial of minimal degree right, and with complex coefficients, as I see lambda, right? So this is the polynomial minimal such that M of A of A is the zero matrix. So this is called, so this guy is called the minimal polynomial of A. That's what it is. That's the definition. Well, we will see some properties about this. You will see that something happens. There is a relationship between the characteristic polynomial and the minimal polynomial. There is a so-called Frobenius theorem. But anyway, we'll get to this. In fact, let's say it right now. The very important theorem. which is due to Frobenius. In fact, today we will see another result of Frobenius, which says the following. It says that the characteristic polynomial P of A, so characteristic polynomial, and M of A, minimal polynomial. So the characteristic and the minimal polynomial have the same irreducible factors. This is important. Anyway, we'll see immediately what do I mean by that. Let's see an example. How do we compute the minimal polynomial of a matrix? So example, I want to show you a quick example, and then we'll get going with some other stuff. So let me consider so let A be the following. Let me cook up a 3 by 3 matrix. Let's say 0, -1, -1 is 0, 0, and 0, 0, 1. So this is in M3 of R. Clearly, these are, in fact, even in C, but anyway, it doesn't matter. So it's in M3 of R, right? And now we would like to compute, so find the minimal polynomial of A. Find, let's rewrite it in this way. Min, right? M of A. Okay, let me. That's what we want to find the minimal polynomial, right? Minimal polynomial. Okay, so let's do this. Well, first of all, we need to compute the characteristic polynomial. In fact, so the characteristic polynomial is given by so it's P of lambda is the same as, so this will be, I think this is pretty close, so this would be, anyway, it will give us something like lambda -1 squared times lambda plus 1. Okay, and now we're going to do the following. We're going to look at the divisors. So now we look at the divisors, right? We look at the divisors of the characteristic polynomial. This guy will be, oh, okay, I already said it. All right, so we're going to look at the characteristic polynomial, the divisors of the characteristic polynomial. So what are the divisors of this? What there will be like one will divide that product, then we'll have lambda -1, then lambda plus 1, then what else? Lambda -1 squared, then lambda -1 times lambda plus 1. What else do we have? Is there anything else left? Well, why not the polynomial itself? I hope I'm not missing anything. So we have 1, 2, 3, 4, 5, 6. We have 6 divisors. So the minimal polynomial right, MA of lambda. So this guy will be the one of minimal degree, right? From the divisors, of PA of lambda. All right, that's beautiful. But now we have to pick which one is good. But this matrix has a following property. But since the square of this matrix is nothing else than just the identity, but since A squared equals the identity, it follows that. In fact, I'll leave this to you as an exercise. Well, it's a pretty easy exercise, but it's worth checking out. Okay. Since A squared is the identity, it follows that that A, how should I say it? Follows that lambda is a root of the equation, let's say lambda squared minus 1, right? And since and 1, lambda minus 1, lambda plus 1 do not have A as a root, right? Sorry, here it's A, not lambda. And these do not have, sorry, do not have A as a root. Anyway, so it follows that the minimal polynomial MA of lambda is nothing else than lambda squared minus 1. Okay, that's it. All right, I hope this example makes sense. So the main key was deciding to observe this guy here. And then you'll figure out that this is nothing else than just. All right. Well, I would like to point out a corollary. I said Frobenius, but you see the characteristic and the polynomial have the same irreducible factors. Well, in particular, this means that, so let's see, corollary of Frobenius theorem. Corollary, which says the following of Frobenius theorem. Which says that MA divides so the minimal polynomial will always divide the characteristic polynomial, and moreover, the degree, as obviously, is less than n. All right, so this is the story with the minimal polynomial. You will see in some applications we will use this. Maybe I'll do some, we'll see, maybe in the recitation I'll use this. But now I'd like to talk about the rank of a matrix. Man, I'm doing too much theory, but anyway, the rank of a matrix. So let's see, definition. In fact, I'll give you a bit of a different definition that you know from. So the rank of an arbitrary matrix, let's say, so the rank of an arbitrary m by n matrix A, right, is defined as as the number. So let's write it like this. So as the number of non-zero rows in any of its row reduced echelon forms. Of its row reduced forms. So that's what the rank of a matrix is. Usually it's not defined like this, but usually it's defined, well, this coincides, is the same definition as the dimension of the subspace generated by its rows, or the dimension of the subspace generated by its columns. Anyway, you can say that this is the, should I say, the dimension of the subspace spanned by its rows or columns. Anyway, it's the same thing. Well, there are some properties here. Well, one property is quite obvious from the definition, is that, so properties of the rank of a matrix. And the first one, which is important, is that the rank of A will always be less or equal than minimum between M and N. That's always going to happen. It's not going to be. And moreover, rank of A is the same as rank of A transpose. Right? Another important results, well, if an n by n matrix A is invertible, then the rank of A is n. Well, that's obvious. And now let's see two more properties. Well, okay, so the rank is subadditive, right? Which means that the rank of A plus B is less or equal than the rank of A plus the rank of B. So that's very important inequality. Okay, and the last one, let's say, well, we have more general, but let me, with what we call the Sylvester's inequality. Which says the following: the rank of A, we have a lower bound for the length of the product. Plus rank of B minus n is less or equal than the rank of AB. And this guy is less or equal than the minimum between rank A and rank B. This is another inequality, very important inequality. You'll see some applications. All right, I think this is the theory that I wanted to do on my 7 pages of theory. Now let's do some problems. The first one that I have in mind is the following. Let A be an Mn of C. fact, let me write it like this. So it's problem 1 here. Such that, in fact, show that we have the following. The trace of a to the power k of all powers is 0, right? For all k going from 1, 2, all the way to n. This is k here. If and only if a is nilpotent. In fact, I would even say a to the power n is directly 0n. Because we can prove that if a is nilpotent, then a to the power n is actually the 0 matrix. So how would we prove this? So we will try to relate this to the eigenvalues, right? So let's see. In fact, I want you to think of this problem for a bit. Think about it for 5 minutes until I'll be right back. So let's see. Oh, sorry about that. Had a small emergency. Okay, let's see. How would we approach this? Well, there are two ways of approaching this problem. Well, maybe I should show you the, I don't know. Oops, there are two of them. There is one approach using Newton's identity. Well, as you can see, we solved this problem, right, implicitly for 2x2 and 3x3 matrices, remember? Or 2x2 is quite clear because we can express the trace of A and the trace of A squared. Especially the trace of A squared, we can express this in terms of what? In terms of the determinant, right? The determinant of A. Is it clear how we do it for 2x2 matrices? So Cayley-Hamilton says that A squared minus trace of A times A plus the determinant of A times the identity is 0. So the only thing we need to prove here is to say something about the trace of A and trace of A squared, because the determinant can be expressed in terms of the trace of A and trace of A squared. So if we prove that, right? So, and for 3x3 is the same thing. But now it's more general. So we have for n by n matrices. So what should we do? Well, like I said, there is a solution using Newton's identity. And in fact, maybe I should show you two ways of doing this. Yeah, actually that would be the way to go. Let's say solution 1. So now let me consider the eigenvalues. So consider the eigenvalues lambda 1, lambda 2, lambda n of A. So I'm considering these eigenvalues of my matrix A. Then, by the spectral theorem, lambda 1 to the power k, lambda 2 to the power k, all the way to lambda n to the power k, right, are the eigenvalues of A to the power k, right? You agree with me? Okay, so this means that we have the following. So we know that the trace of, so we know that the trace of A to the power k is 0, right? Okay. Well, I'm just going to prove this implication. So, okay. So I want to make myself clear. Right. And then the other one, maybe I'll leave it to you. So we know that the trace of A to the power k is 0 for all k1, 2, n, which is equivalent with, which can be rewritten as this can be written in the following way. So I'm just going to write here the system of equations. So this would be lambda 1 plus lambda 2 plus lambda n equals 0. The second one will be lambda 1 squared plus lambda 2 squared plus lambda n squared equals 0. And we're going all the way down to lambda 1 to the power n plus lambda 2 to the power n plus lambda n to the power n, right, will be 0. We have the system of equations. As you can see the system as, let's say, well, but we have to rewrite it in a certain way so that you can see it. Okay, let me not call it yes yet. and- or let me write it in this way so that we can make it look like a system. So do the following. So lambda 1 times 1 plus lambda 2 times 1 plus lambda n times 1 equals 0. Then I'm going to take lambda 1 times lambda 1 plus lambda 2 times lambda 2 plus lambda n times lambda n equals 0. Then let's go another one, lambda 1 times lambda 1 squared plus lambda 2 times lambda 2 squared plus lambda n times lambda n squared equals 0. So as you can see, the coefficients are the same, or lambda 1, lambda 2. And this will be the variables, these guys here. These ones from here. This is lambda 1 from here, then, right? So these will be the coefficients, right? And we keep going to the last one, which will be lambda 1 to the power n minus 1 plus lambda 2 to the power n minus 1 plus lambda n to the power n minus 1 equals 0. And well, this is a system, a homogeneous system. This is homogeneous. Okay. And it follows that, so that this guy, this lambda 1, lambda 2, lambda n is a solution right, of the system S of S. So when is this a solution of this system? Keep in mind this is a homogeneous system, so we have to take into considerations two things. If the determinant of this system is 0 or it's not 0, right? And something happens when the determinant is non-zero. So delta so the determinant of S is given by this guy delta, which is this will be a special matrix V of x1, x2, xn. We'll call this van der Monde matrix, van der Monde determinant. And let me say who this guy is. We're going to look at the coefficients. Look at these guys here. So it will be formed by these coefficients. And this would be nothing else than just 1, 1, 1, lambda 1, lambda 2, lambda n, all the way to lambda 1 to the power n minus 1, lambda 2 to the power n minus 1, lambda n to the power n minus 1. So this is what we call the van der Monde's determinant. Right? Okay. So this will be the, and now we have two options. So we have that if the determinant is non-zero, if delta is non-zero, then the only solution we have is the null solution, right? So then lambda 1 is the same as lambda 2, is the same as lambda n is 0. Right? And clearly from by the Cayley-Hamilton equality it follows that let's see what does it follows what follows that a to the power n is O(n), which is exactly what we want. But now let's see what happens if the determinant is 0. If the delta is 0, so we want to see what's going on. So let's see what happens here. So if the Vandermonde is 0, we can actually compute it, and I'm going to leave it to you as an exercise. So then this determinant, then V of lambda 1, lambda 2. What you can do is without the computation of Vandermondes, right? But maybe I should say it. So this guy is 1, 1. Okay, oh, sorry. This guy I already said who it is. It can be computed, and I'll leave it to you as an exercise. Is a product of all lambda I minus lambda j of 1. Leave it to you as an exercise. Try to use induction. And then when you do the inductive step, you go from n to n plus 1, you expand over. Did you guys see this before? Certainly I haven't done it in linear algebra. Jack, did you see this before?
Yeah, I've seen it before.
Oh, you've seen it before, right? Anyway, usually it's done in an intro to proof class or in a journal setting. Well, this is the Vandermonde, right? And from here, it's quite clear that we have again the null solution. So it follows the lambda 1 equals lambda 2. Well, I'll leave it to you as an exercise to figure this one out using this equals lambda n equals 0. Right? And again, this will follow that a to the power n is 0n. All right. So this is how we use by manipulating eigenvalues. But there is another way. Oh my! I want to show you that other way as well. Solution 2 for this implication. Is it clear what I'm saying, Jack? Is it clear?
Yeah.
All right. That's good. What about others? Timothy?
Yeah.
Okay, that's good. Now I'm going to use something, well, it's quite unexpected, what we call the Newton's identities. And it will follow immediately from this. This is me dropping the atomic bomb, but anyway. So what's this all about? So let's consider, let x1, x2, xn be variables, right? And we'll denote for k greater or equal than 1, we'll denote the following. So pk, p sub k of x1, x2, xn is equal to this sum. Right? Okay. Well, as you can see, this rings a bell already because we had a trace of a. And now for k greater or equal than 0, what do we have? So we have that we denote by e sub k of x1, x2, xn. The elementary symmetric polynomial, the kth elementary symmetric polynomial. Right? And now we'll define them in the following way. So E0 of x1, x2, xn is 1. E1 of x1, x2, xn is the sum. E2, let me write another one, and you'll see the similarities. This will be this sum. Okay, so this is the sum of I equals 1 to n of xi. And this is this sum. Right? And we keep going. We reach to the last one. And this would be the product of xi, with I going from 1 to n. So these are the elementary symmetric polynomials, right? Then we have the following equality. We have this. We'll write it in this way. K times a sub k of x1, x2, xn is the same as the sum from I equals 1 to k of -1 to the power I minus 1 times e sub k minus I of x1, xn times pi of x1, xn. So these are the Newton's identities. Keep this in mind. Right? These are Newton's identities. And you can express all these, as you can see, I can express the kth elementary symmetric sum in terms of the PIs, right? So that's the identity you need to know. All right, now let's get back to our problem. We want to use this, and you'll see how immediate this would be. Again, by the same token, the trace of a to the power, so we know that the trace of a to the power k is 0, but this is also the sum of lambda I to the power k with I from 1 to n, right? And now, for each k greater or equal than 1, that's each k greater or equal than 1, right? Denote this guy pk, right, as lambda 1 to the power k plus lambda n to the power k. Also, we know that E1 is nothing else than the sum what else? E2 will be, so if we look above, okay, it will be the sum of lambda I, lambda j, right? And we go all the way, the last one, En, will be nothing else than just the product. So these are the elementary symmetry. So these are symmetric polynomials, if you want, in variables lambda 1, lambda n. So can you tell me what do we get from Newton's relations? What do we get? So since we know that all these are 0. So what do we get from, since we know that all these pk's are 0, what do we get from Newton's relations? So since P1 is the same as P2, is the same as Pn equals 0, right? In our case. By Newton's identities, we have the following. What do we have? So E1 will be P1. 2E2 will be what? E1, P1 if we plug it in, right? Newton's identity. Okay, so 2E2 will be E1, P1 minus P2. Wow. And we keep going. In fact, let's write another one so that you can see how this is 3E3 will be what? Will be E2, P1, right? Minus E1, P2 plus P3. And we keep going like this. So we have the last one, we have E and E sub n will be E sub n minus 1 P1 plus, oh, sorry, minus because it's in P1 minus E sub a En minus 2 P2 plus, and we so on, we have negative 1 to the power n minus 1 Pn. Well, from this we deduce, and it follows that. What does it follow? That all EIs are equal to 0. Right? So this is equal to 0, then basically we're done, right? So this implies that the characteristic polynomial of A is PA lambda of lambda is lambda to the power n. And from here it's quite clear, so it follows immediately that by Cayley-Hamilton, so this is the missing ingredient here, Cayley-Hamilton, it follows that A to the power n is, and that's it. Is it clear for everybody? That's a very nice one to use Newton's identities. Did you see this before? Like, Jack, did you see this thing with the Newton's identities?
Yeah. I saw that in Foundations 2 and the algebraic number theory class.
Okay. Okay. Nice. Anyway, it's the problem. I hope it's clear, right? The one implication, the direct implication. For the inverse, well, you have to use some kind of some things about use the definition of the eigenvalue, and you want to see what does it mean for to be an eigenvalue of A to the power k, and then you'll see what happens. And either way, I think I'm going to stop here. I think I'm going to do another video. Well, I will explain. I will continue. I will prove the other part of this, and then I will do some other problems as well. I had more problems prepared here. I want to do an application of this thing with the trace and so on. Okay, Thank you very much, guys. I think I'm going to stop here, and we'll see each other this Thursday. All right.
Thank you.